Okay, you know where to how to do the beam calibration, monitor chamber calibration under reference condition. Now we want to move on to actual treatment fields. How do you treat the patients, or how do the dosimetry of the patient treatment fields or non-reference, any field which is not exactly same as you use to do the reference dose calibration. So that's what we are going to do. Nowadays, everything is computerized. You have a computerized treatment planning system, so you use it. So one of the major tasks of the commissioning process is to model the beam in your computer, okay, and that requires a lot of dosimetry measurement, because eventually what you give to the computer to model your beam, that determines how accurately you are calculating the dose for the patient treatment fields, okay. So I give it a name with dosimetry under non-reference conditions. So you have to know what is your treatment planning system. You have all, it is not an easy process, that every system has some advantage, certain disadvantage. You have to choose whatever the best, and then get that system, understand the treatment planning system. And one of the things you do first, is look at what are the data you need to configure the treatment planning system. We will go through two examples. One is Eclipse treatment planning system, which is one of the widely used treatment planning system for proton therapy. The other is Ray Station. Okay, so we'll see what the beam data requirements for. Now everybody is moving into pencil beam scanning. So I'm not sure that whether we should know how to configure a passive scattering beam or not. From historical perspective, I'll quickly go through it just to see what data you need for a passive scattering beam, what data you need for a scanning beam. Okay, let's move on. Connect something here. Yeah, thank you. Okay. So first thing, you have to read the manual of the treatment planning system, and then find out what are the data needed for commissioning the treatment planning system. Okay, what I was talking is, okay, the models that is used for passive scattering beam and for the scanning beam. Initially, these models are called pencil beam models, analytical models. There is analytical the formula that how the dose is calculated. That was used for a long time. Now there was some problems with that analytical dose calculation model, specifically with the energy observer that I talked that to bring the dose closer to the skin. When you put that energy observer, somehow the analytical model had some issues. And then for inhomogeneity calculation in dose in inhomogeneity media, because that was not very accurate, specifically for long. So even for putting long patients in clinical trials, it was not allowed if you are using analytical model, because the dose calculation can be as much off as 5 to 7%. So that's why eventually the treatment planning systems moved into Monte Carlo simulation based dose calculation. So Monte Carlo, I'll talk about Monte Carlo. For Monte Carlo modeling of the beam, you don't need that much data. You just need to have enough data to configure something called a phase space. In the phase space, you have your machine, that how the machine, the source looks like at a after the beam is extracted. Okay, even you don't have to go through modeling the components in the nozzle. So because eventually the data, the parameters of the Monte Carlo are adjusted in such a way that it matches your experimental data. So that's why you don't need to give too much of data to it, because if you have certain amount of limited number of data, then the model has a parameters to fit the model parameters well, and then of course you verify. The important thing in commissioning a treatment planning system is to make sure that it is working on all clinical conditions. But the clinical conditions, the clinical treatment fields are so different from patient to patient, it's very difficult to verify all of them, but you do as much as possible. And that's why at our place, we have not abandoned doing every patient field measurement. So every patient treatment field designed by the treatment planning system is measured, just to make sure that, okay, treatment planning system is not doing something crazy. We'll come out, we'll see what we are doing to verify the dose that's planned by the treatment planning system. I'll talk a little bit about Monte Carlo simulation. There's nothing much to talk. You can talk Monte Carlo simulation for days, okay, but I'm not going to go into that. It's not necessary. Unless and otherwise, you are going to do Monte Carlo simulation yourself, okay. There are many free packages available. We'll discuss a little bit in details when you go to Monte Carlo simulation. Then important thing for us is what are the measurement devices. What devices you are going to use to measure those data, okay. But you have to know what you are measuring and how you are measuring, and then of course, as you have seen, the pencil beam profiles is very narrow, very narrow. Small field dosimetry is a challenge for the physicist, because the detectors are big, field size is small. You can of course use films. Films are very good for doing measurement of a small field, large field, all kinds of things. But film measurement is very tedious and it has its limitations and all kinds of. I'll give you some example. So anytime you are doing a measurement with a detector, which has every detector has some size, okay. The smallest, those like diode is only sub-millimeter size. In that case, the detector size effect may not be that important, but there are other effects, because diodes are solid state detectors. They have a different response to different beams. So you cannot assume that what you are measuring in one field is going to be good in for other field, specifically for photons, because the photon energy, the response of the diode to the photon energy matters. If you have a large field, there are large number of scattered small energy photons. So the diode response will be different, okay. For small fields, you don't have many small energy scattered photons. That the response of the diode will be different. So these are the things, is a challenge for the physicist to make sure that how to check the accuracy of your data that you are feeding to the treatment planning system. So you have to have multiple ways of checking it. Normally, we have that luxury because we have many people and many expertise. So now, if you in a small clinic, if you are working, it becomes a challenge. But the good thing is, for the regular, the machines which are widely used, the data is available somewhere else. So that even the manufacturers, they give something called golden data. You take that data, do a spot checking, and if your data at is agreeing very well, you can use the golden data, like a true beam. True beam is used so many places. So many people have done the measurement. The variation from one place to another place is not that much. Specifically on depth, the relative dose distribution, the depth rows and profiles. So you have some reference to go by. But for proton machines, they vary from place to place. Even if the same machine installed at a different location, because of the variability of the configuration, all kinds of things, it can change. So you have to be very careful about it. Of course, physicists are careful. There's no doubt about it, okay? And we love to do measurements. So you have to make sure that your detector that are using the size effect, you try to figure out if there's a detector size effect and how to correct it. And then you just feed that data to the computer, and then you model the beam. There are parameters in the system that needs to be fitted with your measured data, and beam modeling is done, then you do the model verification and validation. That's how the process goes. And why it is dosimetry under non-reference condition? Because the fields that we are using for a treatment field or verification, they are not exactly matching the 10 by 10 field or whatever way we calibrated our chamber. So that's that. So that's why I call it dosimetry under non-reference conditions. Okay, this is beam modeling in a TPS. Eclipse, and most of the TPS uses Gaussian pencil beam model for dose calculation. This is to some extent still true even if you are doing Monte Carlo model. Somehow they also fit their Monte Carlo the spot beam profile to a Gaussian also. So as you, do you remember how the profiles look like, or you want to see it again? Let me see if I can find it quickly, so that you know why Gaussian works very well. I have to go to another. Okay, I have somewhere else. Just give me a minute. And this is recorded, so when you look at it, you will see that I am quickly going through this. Where are you? Too far away. Yeah. At least you have something here. Look at this. This is a spot profile. It looks like a Gaussian. Okay. So where it is not a Gaussian is here. Okay. There are long tails, so that creates a lot of problem. So in spot scanning beam, the patient field dose is calculated by superimposition of or many spots scattered around. Okay, so then these tails of the spot, this profile, they contribute. Okay, so that's why this modeling of the tail is very important. Okay, so that's why I think you can fit it to a Gaussian, but sometimes single Gaussian may not be enough. And from your mathematical physics knowledge or course, you know that any irregular function can be fitted to Gaussian or any kind of a basis. Any function, you have a sum of the sum of Gaussians, you can fit it. But how many of them you want to use? More you use, the more becomes computationally intensive. So there is some approximation has to be done. Okay. Let's go back where we are. You got some idea what I am going to show you. Lot of data. Okay. It takes at least 2-3 months to commission one gantry. So we are going to finish it in 1 hour. Okay. So this is what the formula for calculating dose. This is called the depth dose curve of the beamlet. Then this is the profile function. You know the dose at any point, and you know the lateral profile, how the dose varies on that plane. You can take at different locations and multiply with depth dose, and then you get the dose. Very simple thing. And this is a lateral distribution modeled by a Gaussian distribution with root mean square sigma. Okay, at that point it varies. This function, this Gaussian function or profile lateral distribution varies from depth to depth. As the beam is moving, it is losing energy, and also it is spreading out. Okay, so that's why this Gaussian, the parameter sigma, changes with depth. That's a function of depth. So what do you need to model the beam? You need the knowledge of depth dose curve and the proton fluence, and this the entrance fluence at the air. What is the difference between dose profile and fluence profile? Because I use it, at a different in different situations. What is the difference between fluence and the dose profile? The fluence is basically at the surface. You have no interaction with air, so that is what is the fluence is. Of course, the fluence is the measure of how many particles are there. Then you can also have a fluence. Also, you can calculate at the different depths also. Okay. So, but normally when I am referring to the fluence here, basically it's the fluence in the air, in the incident profile, a profile of the incident beam. Okay. As you move into the fluence, also get at the number of protons, number of photons, or number of incident particles. They are attenuated, they are spread out. That fluence also can be calculated. Okay, but I am talking about here is the fluence at the surface of the surface of the phantom or the patient. Eclipse treatment planning system requires a limited number of both in phantom and in air measurements for passive scattering and spot scattering proton beams. Let's see what are those things. So these are the steps of treatment planning system commission for passive double scattering system, beam data collection. Then Eclipse wants your data to be given in a specific format, because he said that somebody has written the treatment planning software. He has written in such a way that you have to feed the data the way it can read it. So that's called WTCAD format. Those of you who have worked with Eclipse, then you know very well. But it's not necessary for you to know exactly what that format is. Okay. And then of course you have to configure your machine, like what are the energy options, what are the devices that you are going to use, or what is the distance of the source to the isocenter distance, all kinds of things that you have to put the machine configuration and then the beam data into the system, and then analyze the calculation with check the calculation with major data for different fields. Data required, for passive scattering beam, one of the component is the range modulating wheel. I showed you the range modulating wheel, which rotates very fast, 400 RPM at least per minute, and then it shifts the Bragg-Peak curves to proximal distance. So for each RMW, you have to have the specific data to be measured for a passive scattering beam. This is called pristine Bragg-Peak, unmodulated Bragg curve in water thinnest part of the mod wheel and the thickest part of the mod wheel. Then of course it doesn't have to be thinnest, but you know that what depth of the mod wheel it is passing through. In air G fluence profiles, like the longitudinal, how the profile is changing with depth. That means how the beam is diverging. In air cross profile, okay, to determine the virtual SAD. In air half block cross profile. Get on get out table for each SOVP, because when the mod wheel is rotating, there is a get on and off table for that mod wheel, so that it is hitting it can generate a different SOVP. Okay, each mod wheel it can generate different SOVPs of a different width, and to achieve that, the beam is not always hitting the same thickness of the mod wheel for every SOVP. So there is a optimization process in which the vendor has determined that what are the on and off beam getting pattern, so that you get a different kind of SOVP from each mod wheel. This is a little more complex for you to understand at this time, what is that getting on and off table. But the beam is turned on when the mod wheel is rotating at a certain location. Then it is turned off, then again at a certain depth it is again turned on. And why it is done? Because you have to put different materials in the path of the beam to do a good optimized combination of different pristine Bragg-Peaks to create the SOVP you need. For small SOVPs, the beam the amount of material in the beam path has to be very small. As the SOVP width increases, the amount of material you put at the path of the beam increases. So that's why the beam has to be on for a longer time. For a small SOVP, the beam has to be on for a smaller time, because you want to hit only a small part of the mod wheel. So to control that, so the beam on and off table is given to us by the vendor, that how to generate those SOVPs. It takes a long time to validate that. They have given you a table, but you are not sure that whether that is achieving the goal of producing that SOVP or not. So you have to measure the SOVP curves for each gate on and off table to validate that. but you need to have the data. So that's what it is. And then what else you need? The thickness, of course. You are modeling, you are creating, you are using that RMW, and that RMW, that steps have. Do you remember what a range, how the range modulator wheel looks like, or you want to see it again? You remember range modulator wheel? Because I have to go back to show you. Okay, I don't have that one here in this presentation. Okay, if you want, I can show you. How many people want to see the range modulating wheel again? I think you remember. Okay, there are steps which is rotating very fast. Okay, that's all. I'll show you again if anybody wants to see it. I don't have it here. Just move on because I have too many things to talk. All right, and then of course you know what are the other material in the nozzle, like second scatterer is there, fast scatterer is there, and then the monitor chamber is, the beam is passing through the monitor chamber also. As the beam is passing through the monitor chamber, that adds a certain amount of material in the path of the beam. So you have to also provide that information to modeling of the beam. Okay. So okay, let's see what you do the measurement. That's the fun part. Okay, this is what I talked before is very complex to understand without spending plenty of time into it. It's not that simple to explain all those things, but that you will learn if you have when you have to do it, you will learn it. Okay. It's all right. It's not difficult to learn, but it's very difficult to express. That all the things to explain you in detail. It may be my inability to explain you, but it is not that complex. When you when you have to do it, it will be very good. You will be able to understand easily. Okay, we'll see. G-fluence open field longitudinal profiles. This determines the effective source position is derived by fitting the fluence to a inverse square law. You know, many of you have not even participated or done a electron beam dose measurement. So proton dose measurement is very close to what you do for electron beam. Electron is also charged particle. Okay. So those of you who have configured or done measurement for electron beam, for them this should not be that different. Okay. Because you may not have a hands-on experience of doing this, so it becomes very difficult. Okay, so but if you have knowledge when you are going to do it, if you have to do it, it will help you. Okay. Then open field transfers provide to determine the field sizes at different distances, and a virtual source position is derived from the measured beam divergence. Because the Eclipse model needs the virtual source position and also the effective source position distance to model the beam. So that we have to give the data what they require to create the model. Okay. Here's the mod wheel. This is the mod wheel here. You see, these are the steps, different steps here. They are rotating here. So you have to know the thickness of this every step to give it to the treatment planning system where you are doing the measurements. Okay, this the system has to know it. The good thing is all these different ramps here, they are very equivalent. They are very precisely manufactured. They are very precisely manufactured. If they are not precisely manufactured, if there is some change here and here, then when you measure your data will look completely different than what the treatment planning system is predicting. Half blocked field transverse profile. You close you make block the central axis of the beam and do a measurement, and this helps to determine the penumbra width of the effective size of proton source, which is used to calculate the penumbra width of the profile. So that's why you need this measurement. Okay. The lateral penumbra in the air of the field depends on the effective source size at the nominal SID. So that's why you have to do this measurement. Eclipse requires measurements at the thinnest and thick section of the stationary RMW. You have to park it and then do this measurement. Requires special handling for measurements. Okay, so but I have to confess that none of the newer facilities have passive scattering beam anymore. Okay, even registration treatment planning system doesn't provide you a module for passive scattering beam. Okay, so that's, you don't have to worry too much about it. Maybe I should skip it for the sake of time. So those of you who have worked in the clinic, you are very familiar with a water tank. Without a water tank, a physicist cannot do measurements. Okay, so this is water tank, and then probably for depth dose measurements you use Marcus chamber. There's a large number of chambers you may need. So I am showing you here that we have all these kinds of chambers that you need. Then you have a electrometer, all kinds of things. This is the water tank. This is a part of a water tank scanning system. I am not advertising for PTW. There are many systems available. It happens that we have the PTW system, we use it, but there are many, like there are 10 or some companies which provide this scanning water tank system. But what happened is, for doing this depth dose measurements and all kinds of things for proton beams, for so much of so many RMWs, so many options, it becomes very time consuming. So then then some relief came, like that. You see, this is a device which has some ion chambers at different locations. That's called Zebra, at different locations. In one shot, in 2 minutes, less than 1 minute, you can get a depth dose curve. So that water tank measurement is time consuming, tedious, but this gives you some relief. The bad thing is the resolution of these points where the depth dose is measured is very small. Okay, it is very large, because this has about 32 ion chambers located at a different depth, so you can get only data at 32 points. And specifically for proton beam, when there is a large follow-up rapid gradient here, this may not give you the proper data to fit into this one. Okay, so but the good thing is, this is a line here. It's almost a line, straight line. For fitting a straight line, how many points you need? 3 points maximum, 3 points you need. So that's why the Zebra still works. Okay, I was not a fan of Zebra, but my colleagues, they convinced me that okay, the data you take with water tank and this is not that different. Okay, so that's what they convinced me, and we have avoided doing a lot of water tank measurements by using, these are called multi-layer ion chamber arrays, multi-layer ion chambers array, MLIC, and this comes at a very high cost, about $200,000 or something. Okay, so but it helps to get quick data. So what data it helps you to get? The depth dose curves. It helps to get to the depth dose curves. And for doing the water tank measurement, you have to do point by point chamber is moving, you have to scan it. And specifically for synchrotron beam, because the beam is pulsed, to doing a measurement in a slow pulsed beam, you may get into some kind of a trouble, because when the ion chamber is moving in the water tank point by point, if you are not measuring for enough long time and the module is rotating, then you may not get all the modifications within that needed to get the SOBP within that short time. So you have to, that is a tricky measurement. You have to make sure that when you are doing the water tank measurement, at each point the chamber is getting the full rotation of the module. Okay, you have to do some experiment, but this system doesn't require that. The system doesn't require that, because these chambers are placed at a different location, so it can quickly give you a depth dose curve without going through that point by point measurement. So this helps. And then this is called giraffe. I don't know why IBA gave these names of animal strain, that exotic animal names. This is giraffe. The difference between zebra and giraffe is that this has a very large chamber. Inside this, there is a chamber which is about 15 cm diameter, and that is needed to measure the integral depth dose of the spots. Okay, This is a difficult concept, but I'll show you what that concept is. Integral depth dose curves. Integral depth dose curves. That is what you need for a spot scanned beams. So that's why this one, zebra, the diameter of the chamber inside is 2.5 cm. Okay, this is just for a regular depth dose measurement of the broad beams. Broad beams means like the field size 5, 3, 5, 6, something like that. Just broad fields. And this one, giraffe, is for spot pencil beams, for pencil beams. So that, and then you have to also measure the profiles. The profiles can be measured by ion chamber, by putting point by point measurement, or you can take a film, or you can use some other solid state detectors like OSLD, or you can also use a scintillator plate. You can use a scintillator plate, very high resolution, as data can be obtained by using something. These are scintillator plates. These are available commercially from IBA. You see 4 million pixel detectors, 0.2 millimeter resolution, 40 by 40 cm area. This is a very good equipment to use to get the profile measurement. But these are solid state detectors. Their response can change over time. So that's why you have to have a validation by another means to make sure that this device is working properly anytime you are going to do a measurement. Ion chamber measurements are gold standards. Okay, they are the most accurate things. And if you take into account the detector effect, but these things provide you a quick way of getting your beam data. Okay. So where I am now, let me go back. Okay, so I'm showing you the devices that you need to do the beam data measurement. Okay, that's the section I am in. So these are some data that are measured. Can you believe that this measurement was done with water tank measurement? Okay. Water tank measurement, we do point by point measurement about probably half an hour for each of these curves. So we did this measurement, and this is something that this is mod wheel at a thicker depth, and this is at the thinnest depth. So these are data Eclipse needs. So we gave that one, and this is the data, the G fluence for different energy. G fluence means you are measuring in air how the dosage or the fluence is changing as you move along the beam direction. That is called G fluence. In a coordinate system, you have X, you have Y, you have G. Okay, G system, the beam is coming that way. So this is the longitudinal direction. These are the lateral transverse direction. In a transverse direction, we call it transverse profiles. In this way, you call longitudinal profile. That can be depth dose curve, but if you are doing in air, the beam is not attenuated that much. It's just diverging. Because the protons are diverging, the number of protons at different locations will be different, so you will get a different reading. That's why that's what happened. That is needed by the treatment planning system that we call G fluence, and that is in the beam direction. So this is also measured with that one. And then you need in-air transverse profiles. We can use small ion chamber. You can the films needs validation. Of course, you can always do Monte Carlo simulation. Okay, a Monte Carlo simulation has a special place in doing proton beam data acquisition or data validation or commissioning. Okay, we'll come to that. So these are some of the in-air profiles. These are the transverse profiles, X and Y direction for different field sizes. So this is at a different location along the G is equal to 0 on the surface. G is equal to 20 means you take at a 20 cm depth. So these are the profiles you take, and this is the half beam cross profile in air. You can see this, why it is called a half beam, because the other part is blocked. There is nothing there. But then this tail and this function is very much necessary to determine the effective source size, and the effective source size is used to calculate the beam penumbra. So that's this measurement is very important. Okay, so I am showing here, even if you use film, you have to validate it with ion chamber, and that's what we did. We compared some profile with ion chamber, and we made sure that our film data is accurate. Let's move on. And since the measurements we did, we wanted to make sure that the artifacts of film dosimetry or ion chamber, they are properly, they are accurate enough. So we did some Monte Carlo simulation and compared it to make us feel good that we have the whatever data we have measured are also reproducible by Monte Carlo simulation. So this is what we did in the early commissioning process. We created a Monte Carlo model and then compared it. Monte Carlo is not a measurement. Monte Carlo is a theoretical calculation. So that's why because when you do experiment, you might have done something wrong completely. So anytime you experiment, you have to have some intuitive way of verifying it. Either you do hand calculation or you do by simulation, Monte Carlo simulation. So that's what is necessary specifically for proton beam data validation. Okay. So this is, I am talking about Eclipse, but for other Eclipse and specifically our machine, the Hitachi system. But for beam data measurement for other machines may be different. Okay, so you have to know exactly what the data requirements, and you have to find a way how to do a good measurement for that specific machine. So once you get your data for the treatment planning system, you get it, you fit your data in the treatment planning system, but then you have to take other data to validate and the prediction of the treatment planning system. So that also requires some additional measurement. So the commissioning process is not only to get the data that you require to commission the treatment planning system, but also it requires to get the data you need to validate the treatment planning system output. And treatment planning system output is for various different parameters, various different situations. So you have to have enough data to check the way the fields and to match with some of the treatment fields that you are going to use for treatment of patients. So that's why additional data is needed. You need SOVP data, you need profiles at different in water, relative output factor, all those things that you need. So there is a lot of other data needs to be measured after you get the beam data for the treatment planning system. So one of the things that I wanted to discuss in some depth, when you are doing the measurement, when you are doing ion chamber measurement of the depth dose curve, what you are measuring? You are measuring the relative ionization. You have the chamber connected to electrometer, and the electrometer is collecting what? The ionization charge generated at a different point. So you normalize to a point and then you get a relative ionization curve. Those of you who have worked in electron beam, you know the depth ionization curve has to be converted to a depth dose curve. There is some formula that you have to use, that you have to multiply with the stopping power to get into that depth dose distribution, depth dose curve. And what happens, that stopping power changes at a different locations because the energy of the beam is not the same at all locations, and stopping power is a function of the energy of the beam. Stopping power is a function of the energy of the beam. As you move, as you measure as you move the chamber to different depths in water, the relative energy of the beam at that location is not same as at the normalization point. So naturally you have to correct for the stopping power for that energy. And there is a formula available that how the stopping power depends on energy, and then you correct the ionization curve to get a depth dose curve. So the same thing you have to do for photons also, for protons also. Proton is a charged particle, and then you have to do similar correction at different depths. So that's what I wrote here. The depth dose ionization distribution must be converted to a depth dose distribution. Okay. Perturbation fractions are assumed to have a value of a unit at different depths. The perturbations of like say a temperature pressure correction, it's same. But a polarity effect, ion recombination effect, all those things also change at different locations. So you have to correct for those ones. But they are assumed to be one. But how you validate your assumption? You do the polarity factor at a couple of points and see that it's not changing. Then you can assume it's 1. Then you do the ion recombination factor at a couple of places and see that not changing. Then you can assume that okay, whatever the recombination factor at the reference depth, normalization depth, and at different depths are same. So those are things you have to take into account, because the ionization curve has to be converted to the depth rose curve. Why you are discussing this? Because when you measure, you are using ionization chamber to do the depth rose curve, what you are measuring is ionization or relative ionization. But you don't need ionization, you need the depth rose curve. So that's why they have to be converted. The ionization has to be converted into depth rose curve. As I told you during the reference condition calibration condition, you have to multiply with the NDW, the chamber calibration factor, and then you have to multiply with the temperature pressure correction, polarity correction, ion recombination correction. The chamber calibration factor is not changing, okay? But KQ, the quality factor, may change, okay? So that you have to make sure that quality factor is not changing at different depths, okay? And then polarity, the P polarity and the recombination, they have to be also calculated, and they have to be measured, and has to be used in converting that ionization curve to depth rose curve. Okay, needs to be investigated. So you investigate and just validate the assumption. Okay, they are not changing at different points. And this is the beam quality specification. How to determine your KQ we have discussed already. So this is the formula that is suggested by that TRS 398, that a PDD at a different depth is percent depth, ionization percent depth, multiplied by stopping power ratio of the water with the air at that depth, and then at the reference depth. Okay, value of the stopping power ratio as a function of beam quality factor, residual range, can be calculated from this curve, from this equation. Okay, and these are the parameters given in that protocol. I can give you a reference to that protocol. If you are interested, you can read it. Okay, I have that reference. I'll show you sometime. Before you leave, please remind me. I have to give a reference to the IAA TRS 398. Okay, that you need. Okay, that's anybody has time? How time is now? 9:30. Oh, here is a watch. Yeah, I should look at the clock there. Okay, no problem. I don't have to ask you. I have to look there. Okay, thank you. Okay. So this is the formula that is given in that protocol. We will follow that protocol. And when you are doing the depth rose measurement, if the field size is less than the diameter, 2 times the diameter of the chamber, you have to use a smaller detector. Okay, a diameter detector. And you cannot do a measurement, depth rose measurement, where the chamber size is bigger than the twice the diameter. If the field size is less than the twice the diameter of the chamber. This is true for not for protons, but for all kind of external beam measurements, that you have to make sure that the chamber, that the detector that are using is meeting this standard. Otherwise, the detector size effect will be big, and your measurement will not be correct. Okay. So if you are not using a parallel plate chamber, then you have to validate that the other detectors like diode or diamond detectors, they are providing accurate data by comparing the depth rose curve for a field size where you can use the parallel plate chamber. Parallel plate chamber is recommended for electron dosimetry, for proton dosimetry. So all other detectors have some problem, because their response might be LED dependent, their response may be energy dependent. So that's why you have to validate the other detectors that are using are good for your purpose. Okay, by comparing it with ion chamber data. So this is what I did. What we did, we took the ion chamber data, ionization percentage depth, ionization depth curve, percentage ionization depth curve, and converted them to percentage depth rose curve. Okay, so this is PDI, this is PDD. So this is comparing, and for a low energy and different SOBP, this is the PDI and this is the PDD. So how they are calculate this? We use this formula. Okay, we use this formula, then we calculate and this compared. So to make sure that okay, we know how to convert the percent depth ionization to percent DDD, and we didn't find much difference. That was a puzzle for a while. Why? But for clearly there is a difference if you do electron beam, but for proton beam we didn't find any much difference. So that was a puzzle for some time to solve. That why is that? Eventually, the solution, the reasoning comes from this curve here. You see, this is the stopping water to air stopping power ratio as a function of depth dose curve. Okay, you see this is almost this is very small, 1.136, 1.138. Okay, so for proton beam, that ratio at a different depths are not changing. Okay, there is a reason for that, because in the stopping power there is something called a density effect. The density effect means there is a polarization of the medium, then the proton charge is being shielded, and so that's why the number of interactions that happens with a proton has a certain effect of the medium polarization effect, and that correction factor is very high for electrons, and that correction factor is not high for protons. So that's why the relative water to air stopping power ratio does not change much with the residual range. So what is the message? The message is you don't have to convert your ionization curve to depth dose curve for proton beam. That's the message, because unless and otherwise you are measuring at some of these depths, but that still then the difference is so small that you can neglect it. Okay, so all these discussions I made to tell you that for proton beams, the ionization depth dose ionization curve can be used as a depth dose curve. The corrections are very small. Okay, will you remember this? Okay, all right. So these are some of the other measurements we did to validate our treatment planning system. Okay, a lot of measurements, and and these are, you can see, this is the eclipse model here. This is measured. It matches very well in this region, and it doesn't match in this proximal part of the region. Then we are in trouble. What do you do? No matter how hard you try, the eclipse never gave us this good agreement between the proximal part. So there is a question: should we treat our patients or not? So eventually we told our physicians that whatever you see the dose distribution in the proximal region, they are not accurate. Or do you want us still to treat the patients or not? They said, okay, let's continue. Okay, but we didn't see much adverse effect with the patient. So proximal part, the target is well covered. But you can see the measurement is giving sometimes little higher dose than compared to this. So we try to tell the physician the proximal dose, whatever you are seeing, that can be higher than what you are seeing in the treatment planning. Okay, so that's why we treated the patients, knowing that there are some differences in the eclipse or the treatment planning system exactly predicting the dose in the proximal region. Why I am talking all these things? Just to give you a feeling that what goes on when you are doing a commissioning process, what kind of difficulty you encounter when you are doing the commissioning. Okay, it's not always the things don't come out the way you expect. How you are handling the unusual situation. In this situation, it was a challenge for us. So how we handle it? We went to the physicians, telling that the eclipse has a limitation as a treatment planning system in reproducing the depth dose in the proximal region. So that's why the dose you see in the proximal region of a patient, in a patient, may not be accurate. Okay, you have to add up another 5 to 10% that may be getting extra dose. So we have to be careful when doing the planning, just to make sure that with that uncertainties, still we are meeting the tolerance requirement for the organs at risk.
Sir, how much is acceptable? 5%?
No, see, you can see this is not always true for all situations. This match is very good. Okay, this match is very good. So you have to, in this case, is probably about 5 to 10%. Okay. So your tolerance, we suppose we consider 10% uncertainties. So you have to evaluate your dose, actual dose that is given to the patient by increasing the dose what you are seeing from the treatment person by 10%. Okay, and see that within the 10% increase, you are still keeping your the OAR dose under the tolerance. Okay, so there is no fixed on how much difference you accept. The question is, the tumor coverage is always good. The dose that you giving to the tumor is well predicted. This is the region the tumor is, but there are these regions which are outside the tumor, where there may not be any organs at risk, or there may be some organs at risk, and the treatment planning system is under predicting. So you have to keep that in your mind when you are evaluating the plan. Okay, and that's why that you don't treat the patient with one field. You treat the patient from multiple fields. So this entrance dose, this proximal dose uncertainties are distributed all around. It's not going through only one particular region of the patient. Okay, so there are uncertainties, there are inaccuracies. As a physicist, your role is how to mitigate them and give the correct information to the physician. Okay, and eventually, if they find some reactions and all kinds of things, then you may have to be careful. Okay, that's why there are countries like say Taiwan. They don't want you the hospital to treat the patients all at once. You treat a patient, if you are commissioning a new machine, brand new machine, you treat a patient, wait for 3 months, at least to make sure that nothing is happening to that patient. Okay, then only you start increasing your patient load. So there are some, because they are expecting that everything may not be done correctly. There may be something missing. They want to make sure that you are not going to adversely affect the patient treatment, the give some wrong dose and hurt the patient. Okay. Okay, the profiles, they look good. There are some problems in this is where they are not very well reproduced. This is a bone water interface. It's reasonably looking good. And what is this? This is how the depth dose distribution looks with different field sizes. Okay, let's skip that. Let's skip that. So when you are doing treatment planning commission, sometimes because you don't want to put your target in the beam penumbra, so you have to provide some margin around the target. Okay, we'll discuss that while we do treatment planning. So what is that margin? That margin depends on what is the penumbra width. So dosimetrist, the planners, they need to know how much is that penumbra width in order to decide that margin. So we created a curve like this. We created a whatever 80 to 20% penumbra width, and we fit it with a curve, and we used this curve to decide that what would be the penumbra width for that beam you are using for treatment, for designing the treatment plan. And this is a measurement done to validate a patient treatment field. This is aperture, irregular aperture. We measured it, and then you can see how the depth dose looks at different depths. Maybe your question was, when you are comparing a planar dose distribution to the treatment planning system, what is your acceptable criteria? Normally this is done by calculating something called a gamma passing rate. How many voxels of the dose of the plan is agreeing with the measured data. Okay. Normally it is considered 90 to 95% of the voxels or pixels should pass. They should be within 3% or 3 millimeter difference. Okay, with that criteria you use to validate your measurement. Okay, 2% to 2 millimeter is much better, but sometimes you may not meet it. So 3 to 3%, the voxel dose should be close to the calculated dose within a 3 millimeter radius of that voxel. Okay, so that's acceptable, or within 3% of what the treatment planning system is measuring. then you see 90 to 95% of the pixels or voxels are meeting that criteria. That's how you evaluate your comparison, how good is the comparison. Okay, so this is then we are done with the passive beam. We'll go to scanning beam. So it's a good time. You can take a break. Since we started a little late, maybe continue for 5-10 minutes. Then we'll give a break. Okay, 10. Is that okay, or you want now? Okay, that's good. So this is a reference that's available how to commission a intensity modulated proton therapy system. That's a pencil beam system. Okay, a dear child has many names. So people call it pencil beam. Sometimes people call it intensity modulated proton beam. All kinds of things. Okay, so it is actually the scanning proton pencil beam. That's what this report is all about. And there are some practical guidelines that is available that you have to follow to commission the proton pencil beam scanning proton pencil beam. That's called PBS. Okay, if you hear this name PBS, pencil beam scanning, PBS. Remember that term, pencil beam scanning. So what happens in pencil beam scanning? You have a narrow pencil beam. You apply a scanning magnet that is moving around and putting the spots at a different location. Okay, then you have a paintbrush. You take that paintbrush and move around to paint, get a great colorful painting. Okay, whatever way you want. It depends on the skill of the painter also, how to get a great painting. In pencil beam, the dose at a point is a sum of each spot dose at the point of interest. You have spots all around. You are interested in a particular position where you want to dose. So all the spots around that your point of interest are contributing from their tails, from their peak, all kinds of things. So I had shown you that curve, that how they are superpositioned. You know, maybe I'll write down here. Is this a good pen here? So suppose you have spots put all around like this. Okay, there are spots look like this. So you are interested in dose at this point. The dose at this point will come from this is a profile here of this spot that will contribute something. Suppose you have another spot here that will also contribute some dose. Okay, wrong drawing. So something like this. This will contribute some kind of a dose here. So you have to take the dose from each of the spots at this point and then sum it. Then only you can get what is the dose given by all those spots all around, giving you the dose to this point. Okay, that's how it has to be done. It's very simple. Okay, consider a HDR machine. The source is moving to different locations. You are interested in dose at a particular point. So you have to see that how far does the source is from the point of interest and calculate the dose from that source to that point. Okay, so then you see all the points around and that gives you a dose. Some of the points are too far, they may not contribute anything. Some of the points are too close, they will contribute the maximum dose. But all the spots will contribute something. Okay, because these spots have very long tails. And where those long tails come from? From nuclear large angle scattering. When nuclear large angle scattering happens, the protons go far away, but still they contribute some dose to the medium, and that's the long tail happen. Okay, so the dose is modeled by the integral depth dose and two Gaussians. One is Gaussian in the x direction, the other is Gaussian in the y direction. So you take the percentage, the depth dose curve, and multiply with the profile, the contribution of the lateral profile Gaussians at that point, then you give a dose at that point. Okay, that's how you get it. If you have many spots, then you put a summation here. You sum it and then you get the depth dose at that location. Okay, now this brings me to discuss what is the integral depth dose. Integral depth dose is the total dose in gray centimeter square integrated over the whole plane perpendicular to the beam at that depth G. Let me see if you have a curve somewhere. Go back, go. Yeah, here. So this is what IDD is. The IDD is you have a profile function, okay? You have a profile function. The spot beam has a profile, Gaussian profile or Gaussian-like. I will not say that it's a Gaussian profile, Gaussian-like profile. And then that Gaussian-like profile, you integrate over the whole plane, okay? Take that profile and integrate over the whole plane, infinity, all the way, as big as a plane, and that gives you the integral depth dose of that spot at that plane. It's a function of depth. So this is, you can make it x, y, z, but it is given in polar coordinates. So that's how you calculate it. So a person working with us, a postdoc, we gave him this task: take the profiles and integrate it. Take the profiles and integrate it by numerical integrations, and he did for us. So that's why you get the IDD. But you don't have to do, in order to do this method by calculation by integration, you have to have to measure all the profiles. You have to measure all the profiles and then do the calculation. And sometimes it's inaccurate. And but then we don't have to do we can do the measurement. And how do you do the measurement? You have to do such a way that you are getting the whole dose from the profile. And the profiles can be extended up to 10 to 12, 15, 20 cm also. So you have to make sure you have a detector which is capturing everything from that profile. And that's what is done. That's why you need a special chamber to do that. And that special chamber is called this chamber. This is a chamber, it's called a Bragg peak chamber. It's a very large chamber, okay? So this is about 10.5 cm, and sensitive volume, nominal sensitive volume is this much, okay? Its radius is about 41 cm, 41 cm? 4.06. Okay, 4.1 cm radius. So the diameter is about 8.2 centimeters. So you can capture, suppose you have a profile, Gaussian-like profile, something like this. The Gaussian-like profile, something like this. And if everything, all the tail is inside it, then you get the whole integral dose. But for some reason, if the tail is outside, then you don't get it, okay? So that your chamber has to be big enough to contain the whole profile. That's why it is called integral. That's why this chamber is necessary to do it. When we started, this is the only chamber available in the market. So we try to use it. And then the question arose, are we getting everything? How do you verify? So this is what we did. We used our postdoc to do and then we'll stop it now, okay? Oh, okay, I forgot. So he did some integration, we tried to verify it. But then, this is what also happened here. So, we have a Monte Carlo simulation. In a Monte Carlo simulation, you can score the dose any region you want. So, we created a model of the Bragg peak chamber and try to integrate the dose for a region with 4 cm radius, then 8 cm radius, and then 20 cm radius, and try to compare that how this every energy spot, how they are converging. So we found that up to 8 cm and 20 cm, there is some difference, but probably we are better off by using a 20 cm radius simulation, okay? But we didn't have a chamber of 20 cm radius. So because of that finding, then the manufacturers start building bigger chambers. So now there are chambers available which is about 15 cm, and the spot sizes have become smaller. So within a 15 cm chamber, we can get a IDD of all our spots. and the device that I showed you, where is that device? Go back. The giraffe. Do you remember the giraffe? Okay, let's see the giraffe, and then we will go and see how the giraffe eats. Okay, we'll stop. Here is the giraffe. So this giraffe is 112 cm larger electrodes, 2 cm separation, measurement is about 12 cm diameter. Okay, and if the spot size is more than, if the spot profile is more than 12 cm, then it will not work. So you have to add further correction. So what happened is, because of these limitations, most of the data for a treatment planning commission is not taken from measurement. We have a Monte Carlo simulation program that generates the data. Of course, the Monte Carlo data has to be validated. We validate the Monte Carlo data, making sure the model is good, and then use that data. So I'll stop here, and then after we come back, we'll do some Monte Carlo, talk about Monte Carlo. Okay.